Welcome to the RAOB program's Configuration Options, Algorithm Options tab. To see the Algorithm Options tab, we'll first select the Options menu and then the Program Options. Next, we'll click on the Algorithm Options tab. Before continuing, please note that access to this tab requires use of the optional Analytic Program module. RAOB programs which do not have authority to use this analytic module will not allow users to modify any of the displayed algorithm options, but RAOB will, however, use all the algorithm default settings as seen here. These default settings are the most common and popular algorithm options. And even if you don't have the optional analytic module, the help files provide details of the individual parameters. We'll first look at the CAT or Clear Air Turbulence section. And remember, most of these options display a tooltip text line of information, like this. And upon clicking the mouse on each item, they all display extended information in the information text box at the bottom of this panel. And of course, the help files provide additional information. Okay, back to the algorithms options. The FAA, or Federal Aviation Administration option, is based solely on vertical wind shear data. The U.S. Air Force option is based on a combination of wind shear and wind speed data. The next section defines how RAOB calculates structural icing. Before discussing these options, it should be noted that RAOB also calculates carburetor or induction icing, but there are no configuration options for this type of icing. So let's see how this works. First, we'll close this panel and then plot a sounding profile. Next, we'll select the Analyze menu to access the toolbar, and then click on the Carburetor Icing button. And there's the graphic analysis. Then we'll right-click on this button, and we see that there are no configuration options for this parameter. And now we'll click on the Icing button to display its analysis graphic. Then we'll right-click on this button, and now we've been transferred back to the Algorithm Options tab. Okay, let's continue with the icing options. The AFGWC, or Air Force Global Weather Central option, is the default method. This method uses a simple algorithm, which is a function of the sounding's temperature, dew point, and lapse rate information. The Smith-Fettis technique is an older method, which is totally dependent on cloud layers. RAOB will automatically use the cloud data as obtained from the sounding data file, and currently the only cloud data which are directly available from data files are from the BuffKit CFRL data. For all other sounding data, RAOB automatically estimates cloud layers from the sounding's moisture profile. There is a third option where the user can manually input specific cloud data, but this is best seen on the separate cloud video. And now back to icing options. The last option, the U.S. Air Force method, is also an older method, but it does not require cloud layer information. It instead is a function of a user-defined relative humidity threshold value, where icing will only be analyzed when the relative humidity equals or exceeds this threshold. The default threshold value is 75%. For research and forensic studies, this threshold should be altered to match actual observed conditions to properly model the local atmosphere under investigation. Next is the storm motion method. The traditional method is the RAOB default setting, where the user can specify the depth of the steering flow layer and the storm's angular deviation and speed percentage. Note that the angular deviation is automatically adjusted for northern and southern hemispheres, where storms turn to the right in the northern hemisphere and to the left in the southern hemisphere. The optional bunkers method is primarily designed to study supercell storm motion, where only the storm layer is configurable. Next are the saturation vapor pressure calculation options. The default option with respect to water only is the traditional method, where one equation defines how the diagram's wet reference lines and resulting parameters are derived. The alternate option uses different equations with respect to water and ice, where two different sets of equations are used depending on whether temperatures are above or below freezing, since no single equation accurately describes both conditions. Next is the relative humidity with respect to ice algorithm section. The first or default option uses the traditional vapor pressure method, while the second option is also a function of temperature and frost point profiles. And now we'll look at the effective storm relative helicity calculations option. It is very important to note that if this option is used, it will significantly slow down RAOB's performance because it adds thousands of additional calculations to each sounding processed. Additionally, the use of this option directly affects these derived indices, the significant tornado parameter and the supercell composite parameter. When this option is on, RAOB displays a process bar just as a reminder of its activity. To demonstrate this, we'll turn on this option, and when we close this panel, RAOB will automatically recalculate RAOB's parameters like this. That process bar was quick, so we'll recall the sounding to repeat the process. You can also see this option's presence as listed on the Listings Data Analysis tab. So let's close the Listings view and next look at the EHI, or Energy Helicity Index Depth. Values typically range from 1 to 3 kilometers, so the default value is set to 2 kilometers. Next is the wind shear layer depth. This option defines the depth of RAOB's default or standard wind shear vector, where 6 kilometers is the standard depth. We can close this options panel to see this vector on the soundings listing text, but it's not included on the classic data display, so we'll switch to the custom data display, where we already have the shear vector selected, and then apply it. Note that the shear vector is different than the storm motion vector, which can also be displayed on this custom data display. Back to the algorithm options panel, we'll next look at the VGP, or vorticity generation parameter depth. The VGP is a function of wind shear and CAPE. The VGP depth defines the layer used to calculate the wind shear. And, as with all options listed on these panels, the help files and user manual provide additional information. Next is the desert or high plains option. This option is appropriate for soundings that have a station elevation higher than the 850 millibar level, or about 1,500 meters or 5,000 feet. When selected, the 850 millibar temperature and dew point are replaced by the 700 millibar values. The 700 millibar temperature is replaced by the 600 millibar temperature, and the 500 millibar temperature is replaced by the 400 millibar temperature. When selected, the desert mode affects the show alter index, the European S index, and the total totals, cross totals, and vertical totals values. Next is a cloud water or liquid water content option. Note that the cloud weather parameter is only calculated if clouds are detected. And it is also important to note that these values are different from the precipitable water values, which are not dependent on cloud data, but instead are a function of the sounding's moisture profile. The mixing ratio method is the traditional default option, and it uses a simple density-weighted water content algorithm. The newer enthalpy equation option uses the more advanced gamma method. Now we'll discuss the inversion threshold options. These options were not needed with the older traditional WMO soundings, which had considerable vertical distance between data levels. However, with the development of new sounding technologies and high-density sounding data, the vertical resolution of soundings have dramatically increased. In order to eliminate inversion noise when analyzing high-density soundings, these options are useful. The first box defines the minimum thickness of the inversion layer, and the second box defines the minimum temperature gradient needed to detect an inversion. Next, we'll look at the ducting option. For each sounding, RAOB calculates the refractivity gradient, or N-unit gradient. When this gradient exceeds a certain threshold, such as 157 units, then electromagnetic propagation, or ducting, will occur. This option lets the user change the threshold value to accommodate different regions and climates. The last section is the mixing height method, or planetary boundary layer options. You can choose from 3 methods or any combination of these 3 methods to determine the mixing height, or PBL. The parcel method is the traditional default method, while the potential temperature and specific humidity options are more recently developed methods. More information on each method is presented in the text box just below and in the help files. First, we'll select all 3 methods and then see how they are plotted. So let's close the Options panel and access the toolbar, where we can now select the Mixing Height button. Here, all 3 PBL levels are plotted, and the average level is also plotted as annotated by this arrow symbol. Now let's right-click on the Mixing Height button to access the PBL options. And now let's select the option to only plot the one selected, or the averaged PBL level, and then click OK. And now only one averaged mixing height level is plotted. That completes the RAOB program's Configuration Options, Algorithm Options tab video. Thank you for watching.